What's the foot between friends?
In between friends.
Yeah. Okay. I look for
Average female height is like 5'3" or something.
I'm 4'4". I mean, I'm
probably 5'5", but.
Is it?
Yeah, it's somewhere around there.
Here's no.
Because my mom is about that average height. That's exactly.
My mom fits your prediction for average.
Hey, there you go. So.
Okay, you ready? Yeah. All right, now next, the final speaker for the day is Timothy Parker.
All right, thank you all so much for coming out. Thanks to Vlad for organizing and having me here. I know most of you, so I'm going to keep the talk fairly informal. Also, this is pure math, and so I'm not like inspired to make a lot of money or be super professional, so I'm going to be kind of casual. And better yet, this is geometry, and a lot of geometers are pretty lax about how they do their talks, and so this should be a lot of fun. I'm hoping that everybody will have a nice takeaway by the end of this, regardless of if some of the technical content gets raised. So today we're going to be talking about this guy named Poncelet, this thing called Bezout's theorem, and Poncelet's Porism, which was a famous math result in algebraic geometry. Happened in the early 1800s. So kind of up until the 1800s, mathematicians didn't know what to do with the complex numbers. There wasn't a geometric construction for the square root of -1, and so people threw it away. And even Euler would like write proofs of his theorems with complex analysis, and he would kind of have to reprove things a second time without using properties of the complex numbers until Poncelet came along. So Poncelet in 1812, the Napoleonic Wars had just finished up. He was a military engineer for Napoleon. It didn't go very well for him. And so it turns out he was better, I guess, at geometry than military engineering, so he ended up in prison for 2 years. And in these 2 years, he really created 2 problems and solved 3 major math problems. And so the first one was, why are the complex numbers a geometrically intuitive thing? Why do they make geometry somewhat consistent? The second thing he introduced was, well, it makes the idea of curves in the plane a little bit more consistent, but it leaves out consistency of intersections of curves. And this is something we'll expand on more today. So to solve this problem, he created something called projective space. And then the final thing that he did was he came up with Poncelet's Porism, and that's really the main focus of this talk. And so this is special to me because a friend of mine, Joe Harris, asked me to learn a little more about this and give a talk on it. And so that's what I'm doing today. Okay, so let's start with this idea of geometric consistency for intersections. Given 2 planar curves, maybe something like this, we can see that if we take a line through this curve, that the number of intersections of the line corresponds to the number of bumps in the curve, corresponds to the degree of the polynomial defining the curve. So in this case, we have, I guess, 1, 2, 3, 4, 5. And then this would be, we have 1 hump, 2, 3, 4. And so this is a 5th degree curve, and so we can maybe say that in the plane, n degree polynomials should have n-1 bumps. And we would really want it to be that any line we pick intersects this many times, because then we can characterize general properties about lines and curves. But if we move the line down, we have a problem. We have 1 intersection. And so what Poncelet said was, well, this should intersect somewhere. Maybe it intersects in the complex plane. And for most curves, it does. But complex numbers have this property, and as roots of polynomial equations, if you consider like x squared plus 1 equals 0, the 2 roots of this equation are plus or minus the square root of -1. So this is one example of the fact that complex roots come in pairs. And so what Poncelet constructed was a 6th degree polynomial that intersected a line in the real plane once, meaning that we should have 5 complex roots. And he showed that the first 4 roots were complex roots. But the fifth root that was supposed to be living in the complex plane was actually occurring at a point in infinity, a division by 0. And so Poncelet came up with this idea that, well, maybe we should build a space where parallel lines do intersect at infinity, and maybe this will fix our issue of clean intersection theory. So kind of a more technical motivation for this, and something that Dr. Webb actually gave me yesterday, is the idea of two quadratics, one y equals x squared, and one y is equal to 2 minus x squared. These intersect in the real plane at minus 1 comma 1 and 1 comma 1. Well, if we want this idea of generality, we can move these quadratic curves around, and we can see that there exists a real plane case of 4 intersections, where we would want the degrees of the curves being 2 to result in 4 intersections. This is a degree 2 curve. This is a degree 2 curve. We get 4 intersections. We kind of want this to be a thing. But here we have this case where it's only 2, and we want to know where these other 2 points end up. So Poncelet's trick to turn this into a projective curve and to embed this thing into projective space was to fix a map sending y to y over z and x to x over z. And if we do this, then we get that, well, our first equation becomes y over z is equal to x squared over z squared, and then y over z is equal to 2 minus x squared over z squared. We can multiply up by z squared, get out yz is equal to x squared, and then also get yz is equal to 2z squared minus x squared. And we can intersect these two things by setting their equations equal and get out the equation x squared is equal to 2z squared minus x squared, and this becomes ultimately 2x squared minus 2z squared equal to 0. This is our projective intersection. Well, we want to make sure that if this is really like a bona fide thing, our points minus 1, 1 and 1, 1 are still points of intersection in this projectivization of our curve. And they are, but they're in the case where z equals 1. So z equals 1, y is still y, because it's y over 1, and x is still x, because it's x over 1. So we see that we have 1 comma 1 comma 1 satisfying this, and then negative 1 comma 1 satisfying this. But we really want 4 intersections. But this is only going to happen, I'm claiming, at infinity. Well, what's the easiest way to get infinity in like a Calc 1 class? You divide by 0. Let's divide by 0. So we're going to figure out what this needs to be by setting this third coordinate equal to 0. We're going to say, okay, well, if z squared is 0, or rather z is 0, then z squared should be 0. And so 2x squared is equal to 0. 2 isn't 0, so x is 0. Well, this equation is completely independent of y, and so this should be 1, because we're going to have a line of intersections at y equals 1 and z equals 0. So this is like a line at infinity where this intersection is true. Well, there's kind of a problem with this. I've only written 3 points, right? And this is actually really funny because we worked this out in your office yesterday, and we thought that it was going to look kind of different. I worked through it today when I was doing dry runs, and I was like, wait a minute, the 2 points that we picked out yesterday don't work. So this is a point of multiplicity 2. And the idea is that if these ends tie up together in infinity and these ends tie up together in infinity, it's the same infinity. So they're intersecting at infinity twice. It's really weird. There's a reason for this, which is that if you take these projective equations, so this yz equals x squared, and this yz equals 2z squared minus x squared, and you take the partial derivatives in x, y, and z, and you evaluate it at this point, you get some non-zero ones occurring at y. Namely, the partial with respect to z in both of these equations is 1. And what that actually really gives you is a two-dimensional tangent space at the point in infinity. So this is why we would say that this is multiplicity 2. So these are 4 points of intersection, but it just is a little bit, you need a little bit of convincing to believe that. But we've realized kind of what Poncelet wanted out of this projective space thing. Is that projective space is effectively, Pn is lines, equivalence classes of lines, through the origin in C n plus 1. And the n plus 1 comes from adding this coordinate over Z. So this is where we get the idea. And equivalently, we could write this as coordinates in Cn plus 1. I'm not actually going to write this. There's a lot of words. But we could write this as coordinates in Cn plus 1 where not all of them are 0. Because as long as not all of them are 0, we can divide by the non-zero coordinate, and we can get back Cn. So in this way, we have a way to move back and forth between our complex curves and our projective curves fluidly. And we call this affine slicing. So in the title, I say Bezout's theorem. Right? And this whole time I've been alluding to the idea that projective space is the parameter space where geometry is consistent. So this is kind of backwards. Most people do this the other way. I've said projective space is the space where all curves that are smooth of degree d and e intersect at d times e many points with multiplicity. Most people would say this is projective space, and any two projective curves of degree d and e respectively intersect in d times e many points, and that's Bezout's theorem. So this is kind of like hallmark 1 of algebraic geometry. It's funny enough that it'll get written after being spoken. So that given f and g contained within Pn smooth projective curves of degree d and e, then the number of times f intersects g is d times e with multiplicity. So this is Bezout's theorem, but I would really rather you all think of this as this is true for projective curves in projective space. How am I doing on time?
You good? Yeah, like 5 minutes.
Sweet. Okay. Dry runs are paying off. Okay. So now I want to talk about Poncelet's Porism. And this is really the meat of today's talk, because this is applying kind of abstract stuff to something deep. I'll go ahead and erase these. So among these really cool things that Poncelet built for us, he came up with this problem. In the real plane, given to, nope, this is the part that I'm color coding. My bad, I brought an insane amount of colored chalk here. If you know me, I bring it everywhere, but. Okay, so given two ellipses, we'll call this inner one C2 and this outer one C1 in the plane. If we pick point C0 on the outer ellipse, there are two tangent lines to the inner circle. Let's pick one of them. We push this forward, we call this T0, this is our 0th tangent line. We get a new point on the outer ellipse, call this P1. We take a new tangent line, T1, we get a new point, P2, and we iterate this process. And I kind of picked unfortunate one, but we'll say that it ends up back P. I've never claimed I was a good artist. In fact, I do geometry in a space where you can't draw things, so that's kind of nuance. So we'll call this a circum and an inscribed polygon on C1 and C2. This is a non-convex polygon, but it is an honest to goodness polygon. We have points, we have lines, it's closed, that's what we want. It's inscribed within C1, it's circumscribed about C2. We call this in and circumscribed.
And this will happen in finite time, like if, for the iteration?
Well, so, this is the theorem. So Poncelet's Porism says that given C1 and C2, as we set them up, and a base point P naught, there will exist either infinitely many in circumscribed polygons or zero. And this is completely independent of our choice of base point. So there are either infinitely many of these things in and circumscribed on these two ellipses, or there are none. And it doesn't matter where we start the polygon, it either exists or it doesn't. Yes?
Infinitely many is there's infinitely many that terminate after.
Yeah.
So,
Yes, exactly.
And
Okay.
the two ellipses can be any angle to each other or any
Yes.
center.
Yes. And so really, if we're thinking about this in projective space, which is what Harris and Griffiths do in their paper, really, we're thinking of these as degree 2 curves, so they should intersect 4 times. So I've drawn this in the real plane, but you can also actually picture this in, like so. And so Harris and Griffiths, their result was kind of phenomenal because they did this in P3 for volumes contained within each other, and that's neat. But this is the classical. Okay, so what we're going to do is we're actually going to walk through some of their argument. But we're going to skip over some of the really heavy lifts, and if you're interested in that, I have it prepared, so you can ask me about it after. So the general idea is that we want to set E to be something called an incidence correspondence. And what an incidence correspondence is whenever algebraic geometers want to put together a set of things and describe the solution set to a problem in terms of something, we say, okay, well, we want to pick lines containing points on the outer circle that are tangent to this inner circle. And if we can describe something about the set being finite or zero, then we've described the answer to our problem. So what E, our incidence correspondence, is it will be the points and lines on the outer curve, and then this thing called the dual of the outer curve, meaning it's all the tangent lines to this inner curve. So C2 star, whenever you see a star, means all of the tangent lines on the object. This is contained, yeah, no, that's fine, such that P is on the line. Now, this is where things kind of go off the deep end. So, it's not clear from this setup. This is something called a genus 1 Riemann surface. And what this is it is a complex one-dimensional manifold, meaning that locally it looks like a copy of Rn for some n. And the genus 1 part is particularly important because any genus 1 Riemann surface is structurally equivalent or isomorphic to this thing called an elliptic curve. So elliptic curves are a very famous topic in math, and there's a lot of neat stuff developed about them. Generally, elliptic curve is of the form y squared is equal to x cubed plus ax plus b, and it looks kind of like this. And the idea is that these are a special type of curve because we can come up with a type of point addition. So given a point P with rational coordinates x naught and y naught, and a point Q that's x1, y1, then we can add P and Q by taking the line through the 2 points, self-intersecting the curve again, and dropping down to the other side as access to get P plus Q. And kind of the more interesting case that we care about is if we pick a point on an elliptic curve, and no, that's not a very good point for what I'm about to draw. We pick a point on an elliptic curve, and we want to take, this is our P, new P, and we want to take 2P, then this should just be the tangent line to the curve at the point. And then drop it down to the other side. Well then 3P, so this is 2P. Let's do 3P. Okay. Let's do 4P. It'll intersect somewhere down there. Let's say, for sake of example, that I dropped this a little bit further this way, and we end up back at P again. This is called, well, we would then call P a torsion point of the elliptic curve. So a torsion point really just means that it is a point when re-added to itself a bunch of times, eventually comes back to itself. So I'll write this as a definition. This is kind of important. So P in E is called torsion. If and only if there exists an integer Q, it's QP equals P. For something.
Shouldn't that be 4P, not 3P?
Where? Yeah.
3P.
Yeah, probably.
It should be 4P because you're doing 2P plus 2P. Because if you did 2P plus P, you'd do the intersection.
Yeah, that's a very good point. Yeah.
How is it to not?
Yeah. You can do it by re-adding P and 2P. If you're very
And then you get 3P.
Yeah, if we
So
were
you
to
would
re-add P and 2P, it would just be this, but we would end up here anyways. That's the idea. So yeah, we call this addition, we call this the group law on elliptic curves. And all that means is that given any two pairs of rational points, we can add them together to get another rational point. There's a point at infinity. We're not thinking of this at the moment as a projective curve, but there's a point at infinity that acts like adding 0 to things. So a point plus infinity is itself. And yeah, just don't ask about that. Then, of course, if we have this identity, this additive identity, we should have additive inverses. We do. So given any point on the curve, there's another point on the curve that when we add them together, we get the point at infinity. And then this addition product is associated. And usually we care less about that. Yeah. So Poncelet's idea, and Poncelet's proof and Harris's proof really, comes down to saying that, well, this looks a lot when we have a torsion point. This looks a lot like going around and ending back up at the same place. And we have this established thing that says that this is a genus 1 Riemann surface. And so it maps over somehow to an elliptic curve. So if the elliptic curve that it maps over to has any torsion points at all, their pre-image through this map should be a polygon on Poncelet's Porism. But if the elliptic curve that it maps to has no torsion points at all, then there are absolutely no polygons that are in and circumscribed with two ellipses. Now, proving this is much more difficult than actually just saying that. And really, it's that relationship between the incidence correspondence and the elliptic curve that is like the crux of the proof. But yeah, this is the idea of Poncelet's Porism. So this is kind of neat. I'm working with a guy, Tyler Chamberlain at UC Berkeley. His senior thesis was coming up with an enumerative formula to determine how many triangles there are on Poncelet's Porism. So how many, like, three lines. We're working on quadrilaterals now. So that's kind of fun. Yeah. So if anybody wants to hear more about the relationship between these two things, I'm happy to talk about that after the talk, but I'm not sure that that is like a colloquium audience type thing.
Do we have any questions for Tim?
So okay, you mentioned this is, you get a, you know, if you define combination of points on your curve, you get a root law.
Yes.
This way, and I say, okay, so the point infinity is the identity element.
Yes.
What's playing the role of inverses? Like if you had, like you added P to Q, and then you got that other point down there, you know, somewhere. How do we understand inverses?
Vertical lines. So getting a vertical slope ends up getting you the point infinity.
So they're mirroring.
Yeah, the mirror images, yeah.
Yeah, so like in that example there, that you did,
Yeah.
that first thing, like where is P inverse?
Where is P inverse? Well, right about where the 4 is. Yeah, my bad.
Okay.
So it's mirror images about the x-axis.
So you drop a vertical line, and then when you add those 2 points, you get a vertical line,
Which is 0.
Yeah,
which would be.
yeah, exactly. Because whenever you have the slope is infinity, you should imagine that the point will be. Sure. Dr. T, did you have?
Yeah, I spaced out.
Oh,
I was thinking about that 3P, 4P question, but what's the torsion points?
so yeah, a point on the curve is called torsion if when it's re-added to itself some integer number of times, you get back to the original point.
So like on this cartoon you drew,
It's very
what
good word for it.
would be the, like, can you kind of see where a point with that property would be? That's what I was trying to do.
Not really.
Not really.
You have to kind of take one that works, and then you can like use Desmos and you can say, oh, this works.
So I do actually have a prepared example of torsion if you'd like to see it. So yeah, so the curve,
But so, I mean, this is the whole thing of like in codes when you're doing these
yeah, the discrete log problem.
elliptic points. But so with some iteration, it gets back to itself,
Yes.
and
So
low modulus.
Well,
That's like a constant point.
so there's actually very it's very limited what the torsion subgroup can be. But it's it's basically like if you just keep on adding a point, eventually you get back to where you started,
Yeah.
or you get into a loop.
Yeah, I thought there were like some just classic kind of points out there.
Well, you don't want, so like if you were doing like elliptic curve cryptography,
You wouldn't want.
you want something with that, well, torsion, you'd rather it didn't have torsion,
yeah.
but as long as it has a good sized range, then you're in good. You want to have a lot of points.
So this is like a fixed point.
It's sort of like a fixed point sort of thing.
Yeah.
And the way the group law works is if 3 points are on the same line, they add up to 0.
So you did this in ellipses and getting these cool. I look at that and I'm thinking back to the old fashioned where you have nails in a board and you've got a piece of string going around. But because an ellipse is a conic section, could you do the same kind of thing between parabolas that will come back in some sense, or between hyperbolas?
Yes. So the way that we characterize ellipses, projective ellipses, is you take any quadratic equation in P2, and so degree 2 polynomials. You can represent all of them in P5 by saying, so P2, I'm just totally off, P2 goes to P5, this is called the Veronese map. So you take coordinates x, y, and z, and you map them over to x squared, y squared, and z squared, and xy, yz, and x. And so, yeah, any pullback, some zero set of equations made up of these terms in P5, pulling that back through this map will give you some quadratic surface in P2. And that's how you would view either of these equations.
So you could mix an ellipse and a parabola, for example, because you could build that into your
Well, because
structure.
there's essentially no difference
Yeah.
between them.
They're projectively equivalent as well.
Yep. Looking at the actual geometry of the pictures would be cool.
Also, this is a good time to shout this out. If you're interested in this talk and you like this, I run a seminar on Fridays at 3. And we're going over like just topics in algebraic geometry. And so it's in group 105, and if you want to get on the mailing list, ask me about it. Yes.
So, sorry if I missed this, and this was like the whole point. So Poncelet's Porism, right?
Yeah.
There's this thing. We know that in one of these curves, there's infinitely many or 0.
Yeah.
Kind of, situations that happens. Are we saying that extends to, not necessarily just polynomial, well, yeah, I guess.
Well, okay, yeah, so this is a good question. We're defining this for exactly conics in the plane, in the projective plane, so P2. I'm not aware of anybody trying out any other type of curve in the plane. So I can't answer that question. But I can imagine that you could do a similar type of thing. It just might not map over to something that is as kind as an elliptic curve. That would be my guess, actually, would be that it's a harder problem because you either get some kind of excess intersection or points end up having like some sort of multiplicity, or points on the tangent line have some sort of multiplicity. So one other problem that we're looking at is like if you have a tangent line that wraps back around the point of infinity, you have multiplicity too at that point, but that's technically a bicon. So, yeah, there are weird cases, yes.
Thank you, Tim.
Good moderation.
Oh, yeah.
Moderating. Thanks, Vlad.
So